Swayam Prabha. Digital India. Educated India.
Okay, our last speaker is also virtual. So he's one of the keynote speakers of this conference. So Professor Wu, are you online?
Yeah, I'm online.
So before Professor Wu starting his presentation, I'm going to briefly introduce about him. Professor Wu is an assistant professor in chemical engineering at the National University of Singapore. And his research areas include process control, machine learning, process modeling and simulation, and also process systems engineering. Professor Wu was awarded many awards, including the Best Paper Award in the Mathematics 2021. And he's currently part of editorial board, the Journal of Digital Chemical Engineering. So, and today he's going to give us a talk about the machine learning in model predictive control. Let's give a warm welcome to our speaker, Professor Wu. Professor Wu, if you are ready, then you're going to start your presentation.
Everyone can see my slide? Good. Okay. Thank you everyone for attending this session. I'm very honored to give this keynote presentation in PSD Asia. And today my talk is machine learning in model predictive control. So chemical plant is to transport raw materials products, and we have a variety of objectives we want to meet in running a chemical plant. For example, we want to maintain safety, we want to meet environmental regulations, production specifications, and overall we want to improve the economics of the chemical plant. So in order to do all of these, we need to continuously monitor the process and introduce external intervention, which is basically the process control here. So the objectives of process control system are to ensure stability and safety of the process, to suppress the influence of external disturbances and model uncertainty, and also to process performance. So in this slide, we just show a very basic diagram of a classic control system where we have controller, actuator, process itself, and sensor. So typically in industry, we use proportional integral derivative PID control to design our controller. However, PID control has its limitations. For example, the tuning of PID parameters, Kc, tau I, and tau d typically needs a process model. However, deriving such a process model could be challenging for real-world systems. And also, PID control doesn't account for interactions between process variables, constraints, and nonlinear behavior. Therefore, in 1970s, advanced model-based process control was proposed. So in model-based process control, we have a model that describes the process dynamics, which basically capture the variation of process state variables in time due to disturbances, inputs, and interactions between process state variables. So compared to PID control, the model-based control can improve closed-loop performance because the model accounts for inherent process characteristics such as nonlinear behavior and multivariable interactions. And also model-based control can characterize the limitation on achievable closed-loop stability, performance, and robustness. So here we show the formulation of Lyapunov-based MPC, which was designed to optimize process performance and also guarantee system stability. So MPC in general is designed in the form of an optimization problem, where we want to optimize the objective function L of X and U, which represent the performance index subject to a set of constraints. So the first one is the process model used for prediction. The second one is the initial condition, which is used to calculate the predicted states. And the third constraint is the input constraint. So for Lyapunov-based MPC, we have two Lyapunov-based constraints that are used to ensure system stability. So the first constraint says if the current state is outside of the terminal set rho mean, then we use this red constraint to make sure the system state moves towards the origin. And when the system state enters this terminal set omega rho mean, then we switch to the blue constraint to maintain the system state within this region for all the time. And therefore, if the system state can be ultimately bounded in the small terminal set omega rho mean, then we say the system is practically stable. So MPC is implemented in a sample and hold fashion, which means at every sampling time, we solve the MPC optimization problem, we derive the optimal input sequence, but we only apply the first control action to the next sampling period. And closed loop stability under Lyapunov-based MPC means the convergence to a small neighborhood around the origin. So a key requirement for LMPC or any general MPC is the availability of a process model for prediction. So in the past, people used linear model or linearized system model as the prediction in MPC. However, we know chemical processes are inherently nonlinear, and therefore a nonlinear process model could help improve the closed loop performance. But how to derive such an accurate nonlinear process model is a challenge. Therefore, in today's talk, we will introduce the use of machine learning techniques to develop such a data-driven nonlinear process model for MPC. Okay, so next I will discuss machine learning-based model predictive control from the following aspects. So first, we will discuss the methodology, basically how to develop such a machine learning model for MPC. And then we will discuss the generalization error, which describes the statistical quality of our machine learning model. And then we will also prove the closed loop stability of MPC using machine learning model. And regarding the practical challenges, we will also discuss online learning, physics-informed machine learning, and reduced-order machine learning modeling to address the issues of model uncertainty, data scarcity, and curse of dimensionality, respectively. So we'll first introduce how to build a machine learning model that can be integrated with MPC cost functions constraints to solve the optimization problem. And when we substitute such a model into the MPC, we can also prove the closed loop stability is guaranteed in the probability sense. Okay, so in this slide, we show the class of nonlinear process system we consider in this talk. So it's in the general form of x dot equals f of x plus g of x u plus h of x w. Well, f, g, and h are all nonlinear functions. X is our state vector, U is manipulated input vector bounded by an input constraint, capital U, and W is the bounded disturbance vector. We have the following standard assumptions. So F, G, and H are sufficiently smooth functions. The measurement of process state X are available at each sampling time, while delta is the sampling period. We also assume that the steady state of the nominal system is at the origin. And lastly, we assume there is a controller phi of X that can render the origin of the nominal closed loop system exponentially stable. So here we use recurrent neural network to approximate the nonlinear system in the previous. So continuous RNN model can be described in the following form. Well, X hat is the RNN state vector. U, again, is the manipulated input vector, and Y is a vector of both X hat and U. So A and theta are basically the coefficient weight matrices that will be optimized during the training process. So if we take a look at the RNN structure, we can see there's a feedback loop in a hidden layer. And therefore, if we unfold the RNN model over time, then basically the current state xt, the calculation of current state xt depends on the previous time step xt minus 1, and also the external input ut at the current time step. So this is very much like how we solve a nonlinear dynamic system using a numerical method like explicit order, where we need the initial condition, or we will need the initial condition and the input to solve the state for the next sampling time. So to build a recurrent neural net model, we need to first generate data set. And the training data set could be from industrial process data, lab experimental data, or extended closed computer simulations. So here, the inputs to the RNN model are the state measurement x of tk and manipulated input u of tk at current time step t equals tk. And our output are the predicted states at TK plus PNN, well, PNN is the prediction horizon of neural network model. So for recurrent neural network, all the data points between TK and TK plus PNN are taken as the internal states. And therefore, our model will provide a prediction of state trajectory over this prediction horizon. And here, I also want to mention that the control theory will inform the training process in the sense that closed loop stability condition will impose some constraint on the RN training process, such that the RN model that we derive can ensure closed loop stability. And we use Python and TensorFlow Keras to build our machine learning model and ultimately incorporate the machine learning model in MPC, where IPOP is used to solve the optimization problem. So here we use the RN model as the prediction model in the formulation of MPC. So the formulation of machine learning based MPC is very similar to the one that we show in the previous slide. So the only difference is that we use the RN model as the prediction model here. So again, closed loop stability means the system state will be ultimately driven and bounded into a small terminal set around the origin. All right, so we apply neural network-based MPC to a chemical process example here. So we consider a CSTR with second-order exothermic irreversible reaction from reactant A to product B. And the system can be described by the following two ordinary differential equations. So the first equation describes the variation of concentration of A over time, and the second equation is with respect to the temperature. So by applying neural network-based MPC to such a chemical reactor example, we can see from this figure that by choosing different initial conditions within the operating region omega rho, all the state trajectories can converge to the steady state and ultimately bounded in this small terminal set at the end of simulation. So this basically demonstrates that our neural network-based MPC can successfully stabilize this nonlinear system at its steady state. However, a follow-up question is that although we show that the neural network-based MPC can stabilize the system at some initial conditions we chose at this operating region, we do not know that how this neural network, if this neural network MPC can guarantee closed loop stability for any state within the operating region. So to answer this question, we basically need to derive the generalization error. So generalization error is commonly used in statistical learning theory to measure the statistical quality of a learning model. So as we know, supervised learning is to learn a function from labeled training data. And therefore, for any supervised learning, we can get guaranteed performance on the training data set. However, the challenge for any supervised learning is that we do not know how this learning algorithm will perform on unseen situations. So to answer this question or to address this challenge, we basically need to provide some analysis on the generalization error of our machine learning model. Okay, so next we'll discuss how to derive a generalization error bound for the machine learning model. So to simplify the discussion, here we consider a one hidden layer RN model. So if we write the RN model in the discrete time form, then basically HI in both phases represent the RN hidden state, and XI in both phases represent the external input, and Y is the RN output. So we have the following assumptions for training an RN model. So first, RN inputs are bounded. Second, all the RN weight matrices are also bounded. And training, validation, and testing data set are from the same distribution. And finally, we assume that the nonlinear activation function is one Lipschitz continuous and positive homogeneous. So an example of nonlinear activation function that meets this assumption is ReLU function, which is very popular in machine learning modeling training. So here we first give the definition of generalization error. So it basically calculates the expected loss or error of a given machine learning hypothesis H over some data distribution X and Y. However, since the data distribution X or Y are typically unknown. So people use empirical error to approximate the generalization error based on some data samples drawn from this data distribution. So empirical random maker complexity is used to measure the complexity of a machine learning hypothesis class of machine learning models. So the reason we bring this up is because we will use the random maker complexity to derive the generalization error bound. So in Maurice's book, we have a very beautiful theorem that shows us the generalization error upper bound. So it says given a set of MID samples with probability at least 1 minus delta over some training samples S, we have the following inequality. So this inequality basically gives us the upper bound for the generalization error. So the left-hand side is the generalization error of a given neural network hypothesis class. And the first term on the right-hand side is the training error, right? The training error over some training samples N. And the second term is basically the random maker complexity of our neural network hypothesis class G. And the last term is the function of training sample size M. M is how many data sample we use for training, and delta is the confidence level. So basically, after the training process is done, the first term and the third term can be calculated very easily. So the remaining question is to calculate the random maker complexity in order to derive an upper for the generalization error. All right, so here the challenges for deriving such a generalization error bound are the following. So first, the calculation of the expected value for a complex nonlinear function is difficult. And we know the neural network function is essentially a very complex nonlinear function. And the second challenge is that it's hard to extend the result to vector value functions because originally the empirical random maker complexity was defined for real value functions only. So due to the time limit, here I'll just give a very brief idea of our proof techniques. So to address the first challenge, we basically need the following peeling step. So we peel off the neural network weights and activation functions layer by layer, such that eventually we can represent the upper bound for the random maker complexity as the function of neural network weight bounds and neural network input bounds that we defined earlier. And to address the second challenge, we need the following contraction inequality that can adapt our results for real value function to the vector value functions. So finally, we have the following theorem that shows us the generalization, the upper bound for the generalization error of recurrent neural network models. So although this inequality seems very complicated, but it provides some insights on how to build a machine learning model with a tight generalization error bound. So from the inequality here, we can see that the generalization error bound depends on the following factors. So first of all, it depends on the training sample size M. So basically, if we use more training samples, we will have a tighter bound. And second, the generalization error bound depends on the weight matrices bound and RNA input bound, BX. So this basically affects the calculation of random maker complexity. So to put it in a simple way, basically, if we have a larger bound for RNA inputs and weight matrices, then we have a more complex RNN model. And third point is that the upper bound depends on the RNA input sequence length T. So if we have a much longer RNA input sequence, then basically our error bound also get bigger. And lastly, the confidence level also affect the generalization error bound. So basically here, the theoretical bound can measure how accurately the RNN model is able to predict outputs for unseen data under the same data distribution. So this is practically useful because in addition to the training error that we can see after the training process is done, this theorem here can also show us or give us an approximation of the generalization error for unseen data, possibly the testing data. So next, we derive the following theorem that shows the the closed loop stability of machine learning based MPC using the RNN model that we derived earlier. So consider the closed loop system, x dot equals f of x and u, and we have an RNN model that is built with the number of samples m that is greater than a mn. So mn is the minimum sample size, such that the modeling area between the actual nonlinear system f and our neural net model fnn is bounded by gamma x. Then we can show that for each time step with some probability. Okay, the closed loop stability is guaranteed in the sense that the process state is bounded in the operating region omega rho for all times and can be ultimately driven to our terminal set omega rho mean. And also, I'd like to make a remark here is that the probability 1 minus delta is quite conservative in many cases. However, if we calculate the real probability from simulation or in real world system, then we can see this theoretical result only provides a lower bound for the probability of closed loop stability, and the actual probability could be much higher. And then we revisit this chemical reactor example. So again, our control objective is to operate the CSTR at its unstable equilibrium point by manipulating the inlet concentration, Ca0, and the heat input rate Q. And we did a few case studies to demonstrate the impact of those factors on the RNN generalization error. First, we chose different data sample size to build RNN models. So the figure here shows that by gradually increase the number of training sample used to training the RNN model, our generalization error decreased. So this is consistent with the theoretical result that we derived in the previous slide. And the second case study is to vary the RNN depth and width, which basically are the number of neurons and number of layers. So from the left figure, we see that by increasing the RNN width, the number of neurons per layer, both training and testing errors decrease. And on the right-hand side, we can see that with a deeper RNN model, so we gradually increase the number of layers, the deeper RNN model may overfit the training data when we have very large number of hidden layers. So overall, by increasing the capacity of RNN models in terms of adding more layers or more nodes to the layers, we can improve the network learnability, but also may lead to overfitting. So lastly, we did the closed loop simulation using MPC. So here we examine the RNN model trained with different sample size. So the closed loop results are consistent with the open loop results in the sense that by gradually increasing the training sample size, the probability of closed loop stability is getting higher. So we have a higher probability of closed loop stability with more training data in the left figure. And also in the right figure, we can see that a higher MPC total cost, which means the slower convergence to the steady state and higher energy consumption for RNN MPC if we use less training data. Okay, so far we discussed how to build a machine learning model, specifically a recurrent neural net model for nonlinear dynamic system, and how to incorporate RNN model within MPC. And for that, we discussed the generalization error and closed loop stability in the probability sense. So next, I will discuss a few practical challenges when we apply machine learning-based MPC to real-world systems. So the first challenge is model uncertainty, and for which we will use online learning to improve machine learning model using real-time process data. So we know offline learning models are generally developed using historical data from past normal operations. However, system dynamics of real-world chemical processes may vary over time due to model uncertainty or mode transitions. Therefore, online learning updates machine learning model can capture the latest process dynamics using the real-time data. So the schematic of online machine learning-based MPC is very much like the offline machine learning-based MPC, except that we have a database that store the real-time process data to online update our model from time to time. So here we consider the nonlinear process system with a disturbance term. So we assume this disturbance is not sufficiently small such that closed loop stability cannot be guaranteed in the presence of such a model uncertainty. So we have the following two mechanisms to update our models online. So first, the event trigger RN update says if the decreasing rate of Lyapunov function does not meet our like predefined decreasing rate epsilon W, then we will update the RN model. And the second mechanism is based on the calculation of prediction error. So we calculate the accumulated error between the predicted state XP and the real measurement X. So if this prediction error exceeds some threshold ET,
高德地图开始为您播报前方路况及摄像头。
then it means our RN model cannot capture the latest process dynamics. Therefore, we will use the most recent process data to update our RN model. So these two RN model, the based on event trigger or error trigger RN update mechanism can update RN models when our RN model is detected not perform very well. And next, we will also discuss the generalization error for our online learning models. So online learning basically follows the offline learning mechanism in the way that we have a set of T-label samples. So unlike offline learning that we will train the model using the batch of the entire training set, for online learning we will proceed the model by training by using the data sequence one by one. So we have an initial model, and every time we will receive one input from the real-time process data, and we will do the prediction, receive the true output, and based on the loss, we will update the model. So the question is, how accurately online learning model are able to predict outputs for previously unseen data? So to answer this question, we still need to introduce generalization error into our discussion here. And we also need to introduce another notion called regret, which measures the difference of total loss incurred and that of the best expert in hindsight. So here I'll just show the final theorem because the proof is kind of complicated and which can be found in our most recent published paper in EISH journal. So basically here we prove that the generalization error of online learning model can be upper bounded by the sum of four terms here. So the first term is the regret of the learning algorithm. So for example, if a learning algorithm A has a sublinear regret, then basically this term goes to zero when t goes to infinity. And for many popular learning algorithms such as SGD and Adam, the authors have already proved that the regret has at least a sublinear regret. And therefore, we only need to care about the last three terms. So the first term, or the second term, is basically the training loss. And the third term is basically the difference between lambda t and 1 over t. So lambda t are weight coefficients for our ensemble of online learning models. And the last term is a function of m. M is the bound for the loss function, and lambda is our weight coefficients, and delta is the confidence level. So again, the second and the last term can be calculated easily when the training process is done. So basically, we need to optimize our lambda t to get a tighter bound for our online for the generalization error of our online learning models. So to do that, we design the following optimization algorithm that minimize our training loss subject to the following constraints. So by solving this optimization problem, we will be able to solve the best weight coefficients lambda t that give us a tight generalization error bound for the online learning models. So in the previous slide, we showed the learning with IIT data, which is independent and identical distributed. So this slide, we show a more generalized result, which is online learning with non-IIT data. So this is corresponding to the case where our process dynamics may vary over time due to, for example, disturbances. and therefore our real-time data are not drawn from the same distribution. So again, we derive the generalization error for online learning with non-IID data in this slide. So the main difference between the result here and the result in the previous slide for IID data is that we have a discrepancy term, DISC here, that characterize the empirical discrepancy between target and sample distributions. So sample distribution could be the data from past, and target distribution could be our data in the future. And because of process disturbances, these two data distribution may not be the same. And therefore, we need to introduce the discrepancy term to capture the difference between these two data distributions. And similarly, we have the following optimization problem that optimize our weight coefficients lambda such that we can get a tight bound for the generalization error. So lastly, we apply online learning-based MPC to the same reactor example. So here we assume the historical data is only available for a small operator region around the first static state XS1. And our goal is to operate the CSTR at another static state after the switching time. So this scenario is very common in practice because we know in real chemical plant, we may only collect some data around the steady state operation. However, if we build a machine learning model using this kind of data set, then our machine learning model is not guaranteed to work very well for real-time control, for dynamic control, for other initial conditions. And for this kind of problem, then online learning could be used to improve process model when we receive more data in real time. So here we compile the closed loop simulation results using online learning model all the time and using the online learning model. So the figure on the top left corner shows that for MPC using offline learning model all the time, the system state cannot stabilize at the second steady state. So it will basically oscillate around another set point, which is not the second steady state we define. However, if we use online learning, after a few oscillations and several rounds of learning, then eventually the system state can be driven into the terminal set around the second steady state. So this is more clear from the prediction error plot. So we can see using the initial offline learning R model all the time, the prediction error is quite big all the time. However, for online learning, initially the prediction error is large, but after several rounds of learning, basically we can see that the prediction error for online learning models was controlled at a very low level all the time. And therefore, this means our new or updated R model can capture the latest dynamics of our process model very well. Okay, so next, I'd also like to briefly introduce physics-informed machine learning. So far, all the machine learning modeling technique we discussed are essentially black box modeling. So we purely rely on the process data to build a machine learning model. However, as chemical engineer, we always know some a priori process knowledge. Therefore, a more smart way to build machine learning model is to integrate data and some physical knowledge to improve the model performance. So here we consider the chemical process described by the following nonlinear dynamic system. So one of the fundamental challenge of machine learning model is that it cannot extrapolate well and usually require big data in the training phase. So such a requirement may be unavailable in practice. Therefore, we propose physics-informed machine learning model, improve the generalization performance. So here we design a custom loss function to incorporate physical loss. So the first loss term, MSEX, the blue one, represent the standard mean square error loss function. And the second loss term represent the physical law-based regularization term. So basically in the second term, the red term, we will penalize the right-hand side of the ODE with respect to its left-hand side, such that the model, the resulting machine learning model can not only fit well on the data set we have for the blue loss term, but also can capture the fundamental process knowledge represented by the ODE. So in this way, the physics-informed machine learning model can reinforce learning through the use of physics-based model. And it can extrapolate better outside the training samples because of the physical model that we use as the regularization term. And overall, the physics-informed machine learning model can improve its interpretability. So here we apply physics-informed machine learning model to the same CSTR example. So here we assume our training samples are only generated in a very small region around the steady state. So we only generate a few data points in this green region. And we generate a lot of collocation points to incorporate the physics-based regularization term in the training of physics-informed machine learning model. So by comparing the purely data-driven RNN model, the physics-informed RNN model, PRRN, and first principle model, we show that the PRRN model can capture the nonlinear dynamics better than the purely data-driven RNN model. So this figure, we can see that the profile of physics-informed RNN model is more close to the first principle model. However, for the RNN model, the purely data-driven one, it will deviate at the end of the operation. So the conclusion here is that the PRRN model achieve a higher prediction accuracy than the standard RNN model because of the incorporation of physics in the domain-specific knowledge. So lastly, I'd like to spend a few minutes discussing the reduced order machine learning model. Address the challenge of curse of dimensionality, which means the modeling error will increase with the number of features. So curse of dimensionality happens when we use machine learning techniques to model a large-scale chemical process. So to address this issue, we propose to integrate autoencoder with RNN model. So autoencoder AE is a dimensionality reduction technique consisting of encoder and decoder. So for encoder, it basically maps the input features X in a high dimensional space to the low dimensional space. And sometimes we also call it the latent space. And for decoder, it basically convert the reduced order state in low dimensional space back to its original high dimensional space. So autoencoder itself is an unsupervised learning because it minimizes the reconstruction error, X minus 1. So to integrate RNN with autoencoder, here we embed the RNN model between encoder and decoder. So basically, the RNN model takes the reduced order state X with the manipulated input U to predict the future state XR tilde in this latent space. And after we get the predicted states, then we can use decoder to map it to the original high dimensional space such that we have the states have the physical meaning. So the benefit of embedding RNN model within autoencoder is that now we can train and run our RNN model in this low dimensional space, which can save us a lot of computation time. So in this work, we prove close to the validity of autoencoder based RNN. So the general idea of autoencoder based RNN is that, so originally we have an operating region in high dimensional space, and then we can map this region to a low dimensional space. So our RNN model is developed for this low dimensional space only. And if we can control our state within this omega rho hat, which is the new operating region in the low dimensional space, then we can prove that the actual state of original high dimensional space is also bounded in a closed ball around the origin. So closed loop stability is maintained. So I will skip the details proof here, but the idea is that our autoencoder basically needs to be trained very well with a bounded generalization error bound. So lastly, I will introduce another method for reduced order machine learning model. So autoencoder belongs to feature extraction, which generates a new reduced set of features derived from the original data set. And in addition to feature extraction, feature selection is another important category of reduced order machine learning model. So unlike feature extraction that generate new set of features, feature selection will just select a subset of existing features that exclude irrelevant or redundant features. Therefore, compared to feature extraction, feature selection improve the interpretability of input features since it's just a subset of the original features. So for feature selection, we also have a different methods like filter, wrapper, and embedded methods. So filter methods basically calculate the relationship to characterize the relationship between your target output and input features to find which input affect the output most. And wrapper embedded methods will basically integrate the feature selection process with machine learning modeling process. So compared to filter methods, wrapper and embedded will be more time consuming, but the performance of the resulting machine learning model will also be better compared to the filter methods. So a detailed discussion can be found in our most recent published paper in computer and chemical engineering. So with that, I'd like to conclude my talk. So in today's talk, we first discuss how to use machine learning tools to build a nonlinear dynamic model for MPC. And then we use the statistical learning theory to provide a theoretical analysis on the generalization error of neural network model. And then we discuss online learning, physics-informed machine learning, and reduced order machine learning modeling to address a few practical challenges in modeling chemical processes. So overall, machine learning-based MPC has demonstrated wide applications in chemical, pharmaceutical, and oil and gas industries. But we don't have enough time to show many different applications in today's talk, but we do have a lot of applications in our published papers. So finally, I'd like to thank my PhD advisor, Professor Kripides at UCLA, and my former colleagues and my current students at NUS for their support in this work, and also acknowledge the financial support from the following funding sources. And thank you for your attention. I'm happy to take any questions.
The very theoretical sound presentation. That's why I allowed him to consume more time. So anyway, we are just right before the lunch, but let me take the one or two quick questions. Go ahead.
Yeah. Thank you for a very informative talk.
Sorry, I think you are muted. I cannot hear you.
Microphone. Yeah. You're gonna turn on the microphone.
Okay. Thank you for a very informative talk. One question I have is that in all your proof, actually I have two questions. One question is, in all your proof, do you have to assume that all the state variables are observable?
Yes, we assume all the states are observable.
Applications, this is not the case. So
right.
Can you prove this theorem if we add an observer or machine learning observer to the system?
Yeah, that's a very interesting question. So I want to make it clear that in this talk, we assume all the states are measurable. And in the case that some of states are not measurable, then we basically need to design observer. And in one of our past paper, we also design machine learning based observer, but in that paper, we haven't proved any theoretical guarantees. But if we account for the error of observer using machine learning techniques, then I'm sure we can also derive some theoretical results here. Yeah, thank you.
What about your second question?
Okay. In the second question, during your training or offline training, you do it with open loop data or closed loop data? And what kind of condition you have to impose on the training data, whether you have do it in under PID environment or whatever, or entirely open loop environment, or you have to do it under an MPC environment?
Yeah, thank you. That's a good question. So in the data generation phase, we run populations, and we didn't use any PID or MPC because we only need to collect open loop simulation data to build a process model. And we also consider the operating region omega rho. So we basically choose different initial conditions and different control actions within this operating region to run the open loop simulation to collect the data.
So the control actions are arbitrary.
Yeah, arbitrary, but we also have a bound for the manipulated input U. So we also vary the control inputs within this bound.
Thank you.
Yeah, this is our last question. Yeah.
I have to come here.
Yeah.
Yeah. Okay. Thanks. So in one of your Lyapunov-based MPC, you have a Lyapunov function, correct?
Yes.
So how do you design that Lyapunov functions? Because you do not have a model at all, or you don't have. We assume typically that we have a good model to design Lyapunov functions.
Well, that's a good question. So actually, we don't have any systematic way to design the Lyapunov function. So the way we design the Lyapunov function here is that after we get the machine learning model, the iron model, then basically we need to characterize. Let me show you here. Yeah. Then we basically need to characterize this operating region omega rho, because only in this region closed loop stability is guaranteed. So here's the process. We first derive the iron model using the training data set, and then based on this model, we design the Lyapunov function V and test if V dot is negative within this operating region omega rho. So if it's negative, then we think this is a good Lyapunov function. If not, we just change the P matrix. So our Lyapunov function is designed in the way that X transpose times P times X. So it's in a quadratic form. So we basically change the P matrix to make sure that within our operating region, V dot is negative, such that closed loop stability is guaranteed.
Okay, so it's based on the linear Lyapunov functions, the way I understood.
It's in a quadratic form. Yeah. X. Yeah.
Thanks.
Yeah,
Thank you.
yeah, that's right. Okay, go ahead.
Thank you for your wonderful talk. So, picking up for the question that was asked earlier, since you do open loop simulations as into, for your training data, now I presume you cannot perhaps take inputs wherein the system becomes unstable. But if you take it under closed loop, you can perhaps design a controller that can stabilize the system. So if under closed loop control, if you were to access those zones wherein it's open loop unstable, because it's a non-linear system, unlike a linear system wherein it's guaranteed if you guarantee it in one for a given state. So how do you traverse that? How do you deal with that?
Yeah, good question. So here like I said, we only pick the initial condition within this operating region omega rho. But yeah, we agree that if we have for example, unstable steady state, then without any control strategy, then the system the open loop simulation may be unstable. So to address that issue, we only run for each open loop simulation run, we only run for a very short period of time. So because here our iron model is designed to predict just a few sampling times. So PNN could be very small, just one sampling period, right? So for one sampling period, even if the system is unstable, I'm sure that you start from some initial condition, the system state will not lead too far. So by doing so, then we can recursively run our iron model to predict a very long trajectory. So iron model itself can be just to be developed to predict very short time, but by recursively applying iron prediction, we can still derive a very long predicted trajectory.
Just another quick question. But this is more on the lines of practice. So for instance, even if you have a simple system like a CSTR, what happens to, is there any empirical rule so as to choose the prediction control horizons for a non-linear MPC as opposed to a linear MPC? What happens to the computation time, etc.?
Sorry, can you repeat your question?
I said, so for instance, even if you're taking something as simple as the CSTR example, and you're using, as opposed to the conventional linear MPC methodology, when you use RNN, what happens to the prediction and control horizon? How do you choose them? Do you see any trend? Can you comment on that?
Yeah, that's a good question. I didn't show so this is the result from our AICH paper in 2019. So in that paper, we also compare our model with a linear state space model. So we do show that for linear state space model, although it predict well for a small region around your steady state, but it cannot capture the nonlinear dynamics for the state far away from the steady state. So I think for CSTR, the benefits may not be that obvious because we have a very simple case, but we also did other example like crystallization process, which is a highly nonlinear process, then the benefits of our model would be better.
Okay. Let's thank our speaker again. This is the end of our session, and I think I'm going to resume talk club, right? Okay. Enjoy your lunch.